All right, our next example that we're going to have is the coin change problem. So this is another dynamic programming example. And in particular, it's number 2, and it is about coin change. Now, you might remember that we ran into this idea earlier when we talked about greedy algorithms, how sometimes we could do coin change if you had just the right denominations of coins. You could use it you could just use a greedy approach to minimize the number of coins that you give in change. So just to remind you of the problem, I'm just going to use dollars here to make everything easy, even though these typically wouldn't be dollars, but I'm used to saying that for money. We're going to assume that we have some amount X dollars that we need to provide change for. And then we have some set of coins of varying denominations that are available to make change with. So for instance, we might have, and I'll keep these in some sort of array V, and I'll assume that V is sorted smallest to largest. So we might have something like coins of denomination 1 and coins of denomination, let's say 3, and coins of denomination 4, just as an example. And so if we wanted to have something like if we had $6 and we wanted to give change for $6, the optimum would be to give 2 3s. So if we gave 2 3s, those would add up to 6. If we used a greedy approach, we would first give a 4 and change, and then we'd be left with 2, and so we'd have to give 2 1s after that. Now, I will say that in the coin change problem, it's usually assumed that you have a 1 as your smallest denomination, because that means that things will always finish. You're guaranteed to be able to make change some way, if by no other route than giving all 1s. But you can run this problem without having that example. You can do a coin change problem where you don't have a 1, and what that means is that certain things you would not be able to provide change for. So for instance, if we didn't have a 1 there and we had $2, we wouldn't be able to provide change for $2, and you just have to give that as an example. But let's assume that we've got some array here, V, so that basically V sub I is the value of coin I, and we assume that we have an infinite number of each coin available to us. So this is the denomination of the coin, is the way to think of it. And we can say that I is going to go from 1 to n. So there's going to be n different values of coins. So in the example of 1, 3, and 4, n is 3. Okay, and X is going to be the amount that we have. Now, when we talk about a dynamic programming problem, the way that I will usually end up writing these things, and it's not all that common, is we will just write it as a function dp, and dp is going to have some parameters. And in this case, I know now that it's going to be a 2-parameter problem. And so I'm going to have 2 parameters, a and b. So what I'm wanting to do is define my dynamic programming problem, dp, with a and b, and sort of describe a couple of things. One is I want to describe a recursive way of defining dp, and that means that I need both a recursion and I need base cases. And then I need to actually, in order to do that, I need to know exactly what a and b are. I need to know what the parameters are. And in most dynamic programming problems, the real trick is trying to figure out exactly what does this mean. If you can state this thing very clearly, then the whole problem becomes very easy, because it's just defining exactly what happens in various conditions. So to illustrate that in this problem, I'm going to say that this is a 2-parameter problem. So I'm going to have 2 parameters, a and b. And so in this case, I will say that dp of a and b is going to be the minimum number of coins for giving change for $. So we assume that I have $. That I want to give change for, with denominations of coins from 1 to B available. Okay, so that is going to be my definition of what I mean when I say dp of A and B. So it means the minimum number of coins for A dollars, and I have the values from 1 to B available. And so the solution then, the thing that I will want, the thing that I am trying to solve for, is going to be dp of X, whatever the amount of money that I wanted was, with all N coins available to me. Okay, so this is the thing that I'm going to be looking for. In other words, this is what I am solving for. And then what I need to do is I need to actually figure out how do I take this problem, this DP, and describe sort of base cases and a recursive case for how to define it. So let's think of some base cases first, some very simple things. So if I had something like dp of 0 and n, okay, or actually instead of n, if I just say I for whatever I is, basically how many coins do I need at minimum to provide change for $0 if I have coins from 0 to I? Well, that's always going to be 0. This is a base case. If I've got $0 to make change for, I don't need any coins. Okay, this is hopefully obvious. Likewise, if I have something that's dp of some amount I, and I have none of the coins available to me, then this is going to be something like infinity. And typically in a dynamic programming framework, you would, in this case, I'm wanting the minimum number of coins. Notice that the whole thing is defined to be a minimum. And so infinity means, this is basically not a state you ever want to get to. If you ever run into that state, it's a problem. And when I mentioned before, what would happen if you had cases where you did not have a 1 in the denomination, you would also need to define this in case for cases where the amount of money is less than 0, and make sure that that's infinity. So there's no way to basically give change for negative amounts of money. Okay. So dp of 0 and I is 0. In other words, I don't need anything to provide money, and dp of I0 is infinity. So I don't want to ever get to a state where I have no coins available. Okay, so now the main thing, kind of the key part of this, is I need to write my recursion for the more general case of dp of A and B. And if I think about what my options are, if I need change for $8 and I've got coins from 1 to B available to me, I need to be able to write this as some combination of stuff where there's going to be something over here where I will have db, where I have dp of something that is, an A and a B, where these numbers are lower than the ones over here. They're either the same or lower than the original. So somehow both of these parts have to go down, or at least one of them has to go down in order for this to work. Okay, so notice again that the thing that I wanted was a minimum. I'm trying to get a minimum here. So I am going to take the minimum of a couple of different options. Now, in this case, I'm only going to have 2 options. In general, you might have n options. You might have a lot of different options that you have to choose the minimum of and have to look at lots of different cases. The key is you don't have to look at every case. And just like every dynamic programming problem, you're going to define your solution in terms of simpler solutions, things that are a little bit simpler. Okay, so option number 1 that I have is I can use a coin of the value B. Okay, now if I use a coin of that highest denomination that's available to me, which is whatever the Beeth index is, if I use that coin, then I am left with another dynamic programming problem where I now have A minus V of B. Okay, so remember up here at the very top, we've defined V is going to be the value of the coin itself. So that is how much money is remaining if I use one coin of value B, and I still have all the B coins available to me, and I've used one. So I've given one coin. So that's what this green one here is I've given a coin. This part up here says this is how much money I have left. So this is the dollars left. And I still have all coins available to me. Okay, so this first option right here, the first thing that I wrote, this is what happens if I have used one coin of value B. Now the other option is I choose not to use a coin of value B. Okay, so I'm not going to use that Beef coin, even though it was available. I say, no, there might be another route that's easier. So in that case, I'm left with a new problem where I still have the amount A to make change for, but instead I now have B minus 1. In other words, I have all the coins except that most valuable one available to me. Okay, and believe it or not, that's it. That's all we need for this problem, is what we had here. So let me just review this very quickly to remind you of kind of how we approach the problem. We try to come up with something that is a way of defining dynamic programming as a recursive problem with, in this case, two parameters, A and B, and we can clearly define what that thing is. So in this case, we say the first parameter is the number of dollars we need change for. The second parameter is the number of the coin denominations that we have available to us, starting at 1 up to B. And once we've defined that very clearly, that this recursion is going to be the minimum, then we next determine what is the thing that we need to find a solution for. What is that? In this case, it's X dollars and all N coins available to us. So that's the thing that we're looking for. And then we would define our recursion. We have a couple of base cases here, which are what happens if we have no money, that we don't need to make change for anything. Well, that's the first one. Or the second one is, what if we don't have any coins available? Well, then we'd need sort of an infinite number. We don't ever want to reach that state. And then finally, we define the recursive condition, which is going to define dp of A and B as dp of simpler things. So if you notice over here, we've either reduced the dollars left or we've reduced the number of coins available. So one parameter or the other is smaller in this recursion. It's not the same value, it's nothing bigger, it's something a little bit smaller. Okay, so given all of that we've defined this, we can kind of illustrate exactly what it would take to go through and solve this. And I'll just illustrate this with a very simple example. I'll use the example of 6 that we had before. So that was the example where we wanted x equals 6, and we had that v had the values 1, 3, and 4 available to us. Okay, so the way that this would work is we can often set up a table, and in this case, I will write A over here and B over here. You can sort of do it however you want. Okay, and so B, well, actually, let me just go ahead and create a new one. So I'll start each of them at 0, although often you won't bother to do the 0 element. Zero, 1, 2, 3, 4, 5, 6. Okay, and basically a table like this, I'm going to show you kind of the bottom-up approach to doing things. The top-down approach would fill in the table starting with what we want. Now, what we're looking for here, the thing that we want is dp of $6 with all 3 denominations of coins available to us. So that's the thing that we're looking for. And you'll notice that is this cell right here at the very bottom right corner. So this is the thing that we need to get to. And every other thing that we need for any cell, our recursion that we have up here is telling us it's going to be some cell that's either up above us or to the left of us. Those are the only options that we have. Okay, so let's go ahead and start filling in this table. So the first thing I'll do is fill in some of the base cases. So the case where we have $0 and any number of coins, we can just say we always need 0 coins to handle $0. And the case where we have no coins, well, that's going to be an infinite number of dollars, so that's going to be infinity. And all of these, we certainly don't ever want to get there. Okay, so the first thing we can do now, so kind of I'm going to show you the bottom-up approach, and again, the top-down, you would sort of fill in the table and remember what you got along the way. The first thing we can do is fill in this cell right here, because this cell is going to be the kind of the earliest one, and then we can either work our way kind of across the table heading to the right or down. It doesn't really matter. Either way should work. And we know that because every cell is only going to be looking at stuff above it or to the left of it, or both, above and to the left, everything that this cell needs has already been filled in prior to this point. Okay, so in this case, we're going to be looking for, and I'll write it over here at the side, we're looking to fill in dp of 1, 1. That's what we want. And so we've got two choices here in our recursion. What we want to get the minimum of, the first thing we can do is take our value a, so it's going to be dp of a minus the value of b. So the value of b, the first element there, and I started my indices at 1. I'm sorry about that. So these are 1 to n instead of 0 to n minus 1. So this is going to be dp of a minus 1, which a in this case, notice a was 1 here. So that's actually dp of 1 minus 1. And then b, which is still 1, plus 1. Or the other option is we don't use that coin, and so we're still left with 1, and we have 0. Okay, so what that means is this is equivalent to the minimum of dp of 0, 1 plus 1, or the dp of 1, 0. Okay, and so if we look, and again, I used A across the top and B across the side, so it's probably a little backward from what you might normally think with row and column. But in this case, if A is 0 and B is 1, that's the top one there, A0, B1, that's going to give us this element right here, okay, is 0. So this thing right here, that's going to be 0. Okay, which means that the first thing up here has a total value of 1. 0 plus 1 is 1. The second one down here, dp of 1, 0, that's where a is 1 and b is 0. That has a value of infinity. So this is infinity. Now, obviously, the minimum of those two things, between 1 and infinity, the minimum is 1. Okay, and this should be obvious to you that if you have $1 and you have coins up to value 1 available, it's going to take 1 coin to do that. So that should be, somewhat obvious. Okay, so I'm not going to illustrate all of these. I will just jump ahead a little bit and kind of fill these things in, and I'll let you just see some of the end results of them after we filled in some of the additional information. Okay, for instance, if we take the dp of 2, 1, that's going to be this cell right here. It's going to be the minimum of 1, 1, which is this one off to the left, plus 1, which is 2 coins, or infinity. And obviously, the best answer here is going to be 2. And if we continue this, we would see that these come out to be 3, 4, 5, and 6, which basically means if the only coin available to us is the 1, it's going to come out to be 1, 2, 3, 4, 5, and 6. Okay, so now we go on to the next row and we say, what if we instead had, what if instead we're looking at this cell here? So we want to find dp of 1, 2. And this is going to be now the minimum of dp. And we've got two choices. One is that we can take the current value, which is 1, and subtract off the value of coin 2, which is 3. 1 minus 3, and we still have coin 2 available plus 1. And the other option is we keep ourselves at 1, but we don't use the second coin, which has value 3. Okay, so dp of 1, 1, we've already figured out. This one was equal to, this one right down here is equal to 1. This one up here, this first part, dp of 1 minus 3, 2, that we would treat as infinity because we get a negative number here for our first thing. So this is not really possible. You can think of that as infinity if you want to, but basically you don't want to do that. And that means that the value for this is 1. And again, it's probably obvious, even if you have 2 coins available to you, if you only need to make $1 change, it still costs 1. Well, we can fill this in, and here we would get 2. Let me show you a maybe slightly more interesting one, just to illustrate again how the dp table gets filled in. So if we say dp of 3, 2, now what we want to do is calculate the minimum, and we've got two options here. We can either take the coin of value 3, so this is going to be dp of 0, well, just to write it all out, it's the dp of 3 minus 3, 2, plus 1, or it's the dp of 3 using 1. Now, basically, if we say that we have the dp of 3, 1, this bottom one down here, that's already been computed, that's 3. In other words, if we only have coins through 1 available, we need to make change for $3, we had to use 3 coins. The other option here is dp of 3 minus 3 is 0, 2. Well, dp of 0 and 2, this section right up here, this thing is 0. That's this value right here. Okay, and so this means 1. And this should be obvious that if we need change for $3 and we have the coins of value 1 and 3 available to us, then we only need 1 coin. So in this case, this comes down to 1. And notice that it's interesting that actually we have more dollars in change, we need fewer coins to get there. And so we can do the same thing if we do it with with 3. This is just with these 2 coins available. This is going to be 2, and this will be 3, and this will be 2 available to us. So working our way backward here, this again will be 1 and 2. If we let's look at a couple of other examples here. And you can fast forward if you don't want to see this many examples. But let's go ahead and take dp of 3 and 3 in this case. So dp of 3 and 3. So I will erase all of this. Okay, so if it's 3 and 3, it means we have coins 1, 3, and 4 available to us. It should be kind of obvious that we can do this with 1 coin. But the way that looks is we would say this is going to be dp of 3 minus 3 with 3 plus 1, or dp of 3, 2. Okay, and so, sorry, dp of 3 minus 4. Sorry, on our third coin now as value 4. Okay, so this first one is going to come out to be infinity. So this top one comes out to be infinity, but dp of 3, 2, we've already figured that out. That was just 1. So our answer here is, again, 1. And likewise, now we can actually get something of change 4 with just a single coin. Okay, that's all we need there. If we need to get to 5, that's going to end up taking us 2 coins. So let's look at our very last example. This is actually the solution that we're wanting to get, which is dp of 6, 3. And remember, this is the thing that we care about the most. So the way we can write that is going to be the minimum between the dp of 6 minus the value there, which is 4, 3, plus 1, or dp of 6, 2. Now, what do these two things mean? The first one up here means that we're going to take a coin of value 4. So that's going to be what that plus 1 is for, is we took the value 4, and that's going to leave us with $2 and all the coins available from the first through the third denomination. Or the other option is we don't take the coin of value 4, and so we're left with still needing $6 change, but we only have coins of the first two denominations, 1 and 1, which happen to be 1 and 3 here. Okay, and so if we look at each of those, dp of 6 minus 4 that's 2. dp of 2, 3, that is going to be this number right here. Okay, so this is going to be 2 for this part. And so that option is 3. That means we'd need 3 coins total if we took the 4. The other option is 6, 2, which we figured out before. And that had the value 2. And so this is going to be 2. And so the answer out of all of this is 2. So what we end up filling in our final square is 2. And that means that we can make change for $6 with denominations 1 through 3 with 2 coins. So that's a pretty complete example of how this works. Notice that you could code up this entire process right here. This is just a couple of for loops, 2 nested for loops. And in each for loop, you're basically just doing one comparison. You look up 2 values and you pick the smaller of the 2 values. Now you do need to make sure you handle the case where you get something that that goes to a non-existent amount. If you have like $, or you have or you need something that is effectively infinity, you need to make sure that you handle that correctly. But otherwise, it's a very straightforward coding example. And I will try to give an example of coding this problem up in class just so you can see it. So I hope I illustrated the whole process of doing dynamic programming, from the idea of defining your function at the very beginning to going through and defining your recursion and what your goal is, and then actually coding it up, in this case in a bottom-up format, to solve for it.